Just wanted to start today. My name is Don Jabot. I am a global bar and tubular products manager for Ajax Taco Magnathermic in Emity. Emity's out of Italy. I'm also the chairman of the board of directors for the ITA for North America and South America, which I want to give a big kudos and a thanks to the ITA for putting on this event, Tube 2020. It is a wonderful event with hundreds of attendees per day. The staff at the ITA has worked very diligently since the close or cancellation of Tube Dusseldorf um, just a few short weeks ago. And we put this whole format together, a new format, as we talk about the new normal. This is our new normal. Virtual events, virtual. We're hopeful everything will come back for the physical shows, but I think the virtual shows will be a element forward, and a good element, allowing more people to attend, get more exposure for your advertisement dollars. Hats off to the ITA for Mesa for doing what was right when they canceled the show at a great cost to them. They had a lot of precautions and was really put a lot of effort into doing the physical show. It was just the right call at the last moment. So hats off to them as well. Without further ado, the topic today is going to be induction heat treat, quench, and temper systems. We do ERW as well as seamless. So I got quite a long presentation, several videos to go over. So let's get started. Now, who we are, Ajax Taco Magnathermic, is over a century-old group of companies joined together under a holding company called Park Ohio Industries out of Cleveland, Ohio, USA. Ajax Taco has over 1,000 employees and 20 worldwide facilities and staff with over 120 mechanical, electrical, and metallurgical engineers. We staff this large engineering staff because we've taken the philosophy that we still custom engineer every system that we provide. We have standards in power supplies and different segments, but even the power supplies are custom set up in the outputs for the individual product range and throughput, product mix, whether you have upsets or not. So we still custom engineer every system. And we believe, and I think it's proven, that we're over 100 and some years old and dominant in the world as far as these heat treat, quench, and temper lines for bar and tubing. But today the focus is on tubing at Tube 2020. So without further ado, we'll move on. Here's actually our footprint. If you look at the Americas, that's where Ajax Taco is located. Out of Warren, Ohio is the primary. But as you look to the left, you can see we have global manufacturing facilities all over the world, which typically is made up of a lot of our different brands that we have acquired and put under the Park Ohio umbrella as well. You've got service centers all over the world. And these service centers are not just sales offices with one or two people. These are actually full functioning facilities for aftermarket coil rebuild, spares, leads, parts. A lot of them have service technicians that work out of these facilities. So if you look at the range to the right of the service centers that we have a very good global footprint. Just looking at the Americas, north and south, we've got 45 servicemen and 140 engineers. Before, when I was talking 120, that was just Ajax specific, but we also have Pillar, GH induction, as you can see here to the left. So we got 140 plus engineers in North and South America. The principal engineering and manufacturing facilities here, you can see, are primarily in Ohio, Wisconsin, and New York, USA. and then 13 service and support centers strategically located uh, in major metropolitans of induction customers, not just the metropolitan areas of size of people. But you can see quite a footprint, which includes Mexico, Brazil. It's not shown here, but Canada. We have a very dynamic group out of, it's right outside of Toronto in a little city called Ajax, Canada. They also manufacture the power sources and some handling and things to the Canadian specifications for their ratings. They have a special rating there. CAE, I believe it is. So when you look at Ajax Taco as a whole, a company, induction company, and my product line, which is the bar, tube, and pipe applications. But today here, this list is for tubing. You see we have quite a list of applications for tube and pipe manufacturing. I did another talk here at Tube 2020 on induction applications, this exact page, and it would turn into about 2.5 hours to cover all these applications. So we're well immersed into the tube and pipe manufacturing, well invested. We have dedicated people. Our Emity group out of Italy is our European arm that manufactures products and CE rating, but joint with Ajax Taco, we produce all these applications through our Emity division for the Europe market. Now, I thought it important that we cover the basics of induction, so we're well-rounded here in understanding of how the technology works. And just in general, you look to the right, that is a copper induction coil, doesn't have the insulation on it, so you could see the copper. But there's a magnetic field generated around each individual turn that combines together to make a combined flux that goes all the way around the ID of the coil. So this is, without a product in it, this is a flux mapping. Now, going into the technology, the primary heating is I squared R loss. The same principle as a nichrome wire. You have current flowing against a resistance that generates heat. So that's the primary heating principle here. But there's also, when you get below the magnetic Curie point, a hysteresis heating, which adds to the efficiency. And typically for a 0.3 carbon, that's somewhere around 1400 degrees Fahrenheit, and we're pulsing, like you see on the solenoidal sine wave to the lower left on an oscilloscope, we're pulsing above and below the solenoidal sine wave, the line of polarity. So we're pulsing positive, then negative to make one complete solenoidal cycle. So, typical frequencies here for tube heat treating is anywhere from 600 hertz, that's 600 pulses per second, up to probably 10 kilohertz, which is 10,000 of these cycles per second. Now, when we get up into the high frequency HFI welders, we're up, 500 kilohertz. That's 500,000 cycles a second. So semiconductors play a big part in this technology, but very precise. Again, this is the flux mapping we talked about with the picture to the right, and it just another show to the left that actually shows the workpiece, the tube, inserted in, and how the magnetic field passes through the tube. Now, as we talk about that current inducing into the tube, frequency plays a major role in the controllability and the heating of induction. And we use a reference point called the reference depth of current penetration, as you see to the right. The definition of that is when the current density reaches 37% of the surface value. And this is from the time we turn on the induction we're inducing at this depth of current penetration. And if you look to the left, 60 hertz, you can see a deep depth of penetration through the wall. A 1 kilohertz 1,000 cycles per second is shallower. And then you get up into the 300,000 hertz, the 3 kilohertz, and it's very shallow on the surface case depth. And again, that case depth and reference depth of penetration is gauged in when the current density reaches 37% of its face value. Well, after that, what happens? I mean, because we want uniform delta T from the surface to the core. So conduction then plays a factor in the rest of the heating uniformity. But unlike a gas furnace that we're just hitting on the surface and having to conduct the whole way through the tube, we're inducing current at this reference depth of penetration. And we can pour the coals to it. We can put a lot of current in that area without overheating the surface, versus a furnace or just surface heat. You got to be cautious not to overheat and cause grain growth in your metallurgical grain structure. Now, if you look to the left, this is a little video that shows heating of a rebar about 1.5 inches. And let me play it here, and you will see that, I think, yeah, I hit it twice. You'll see the induction go out, and you see it go on the surface, that depth of penetration. Then it's conducting, and watch the end of this thing. It's just going to normalize out to the core very quickly. And we're talking like 150 degree delta T is what we target. We're heating here to 2250 degrees. See, right there, normalized out. You can see the rest of the color go together. You saw a little cold on the end. There's cold wall conduction running up the bar, solid bar. But if you look at that, very controlled precision heat on the length, and 150 degree delta T on the core to surface. Now watch the side heating through the copper coil here that is insulated. You got cold wall conduction, so we overlap the coil a little bit on this side. The other end, you have radiant losses out the end, so you've got to have an overlap of the copper coil to compensate for that. But there's rules of thumb, and it's very precision set. Usually there's a stop that it comes against to gauge that distance. Now, if you look at how this actually works, and I'll try to stop this, to the right is a FEA analysis of a seam inductor. This is a single turn copper coil right here. And around that is a magnetic field flux concentrator. And I'll show you how that channels the magnetic flux. As we saw go around the turns all the way around, this captures 3 sides and throws it into one direction more efficient. So it's more of a focused flux. So let me run this FEA. Here we go. There. Okay. If you can see my little mouse pointing here. The high intense heat area is actually the depth of current penetration. The current is turned on. The magnetic field then penetrates at that current depth of penetration, and then it conducts through the rest of the wall. And in this case, where we're annealing back the ERW weld to get a common metallurgical structure, we plot a V area, and it's very precise plotted. So we got very good control over this technology, and we got great simulation software. FEA technology is a wonderful tool that we use, common, and we have some people that are experts at FEA. So let me play the rest of this, and then you can watch when the power turns off, how everything just keeps conducting and everything normalizes out. So that's basically how the heating effect works from a single turn. And this particular one, like I said, is a seam weld inductor that I showed under the applications in my other talk. So let's move this forward here. There we go. Now here is another flux mapping. Here's the coil, copper coil winding going all the way around. This is a cross section. But you see the magnetic field and how it crowds together, and we get a depth of current penetration. But what we're trying to show here is a condition called current crowding. Remember in the picture that we showed, the video we showed heating, that there was an overlap. That means, you know, the coil overlapped to the end of the part to compensate for the radiant losses coming out. And this is, again, this is more of a swedging process here, or a heating up for an upset, but it shows this condition. And this condition is prevalent when you're in a heat treat line, when you're feeding the pipes, you must keep them butted together. Now that doesn't mean they're 100%. We've done a lot of analysis and show we can live with some gap, and the field will cross it over. But we're talking a max of a ½ inch is stretching the envelope here. Now, if you look up in the upper right corner, that shows how the fluxes are actually migrating. Each line of flux has a certain amount of current in it. And the more lines of flux you have, the more current you're inducing. So if you're wrapping around the edge with more current, you're going to overheat it because you're inducing more current in the same mass rate. And the corner ends up overheating, as you see here to the upper right. But you can slow this condition down. As you go lower in frequency, the lines of flux go further apart. So you can slow this condition down with frequency. But mainly in the material handling, it has to be precise enough that the best way to do it is get the right frequency for the application and keep the pipes butted all the way through. So here we're going to go through some typical, again, I'm in charge of the bar and tube, and the bar and tube heat treat lines are so similar. We have a presentation lumped together, but I took the bar side of this out for this talk because we're focused on just tubing. But you can see at the bottom, I mean, we do quench and temper lines. Well, that is a bar. I didn't take that part out. But we've got induction tube heat treat lines that's been out there for 7 decades. We've got the oldest one I know of is down in Mexico. It's 58 years old. And we do anywhere from a couple tons an hour throughput to 42 tons an hour is the biggest system we have. We're actually starting one up in January at 36 tons an hour in Houston, Texas, USA. That's where I'm located at. Ajax Taco Magnethermic, and through our Amity group, we can offer install services, which includes all the civil work. To the left, upper left, you see a quench pit for heat treat quench and temper lines. This particular one is very large, but it's for 36 tons an hour. So quite a volume of quench water goes in there. We do all of the motor control centers, the input transformers, switch gear. You know, we're typically working with a 12/4/7 line. You know, we can go higher, but that's not in our necessarily expertise in our wheelhouse we like to provide. There is a lot of people, we're disconnecting to one right now that's 39 kV. They wanted us to connect to 138, but the 39 kV we settled on, and we're stepping it down to an end voltage of 480. At the lower picture is a pandemic view, panoramic, pandemic. We are in a pandemic here in 2020. That's why we're doing this virtual. It's early here in the Central Time, so excuse me there. But this panoramic view shows a complete heat treat quench and temper line that we installed front to back, all the civil work, all the motor control panels, all the plumbing, all the electrical, turnkey front to back. So we do have that capability, and we do have a department that that's all they do. And at Ajax Taco, we do the melting systems, forging systems, heat treating system for automotive, as well as my product lines of the bar and tube lines. Now, when you get into the heat treat quench and temper lines, it's a building block of components in a very large line. So I have this broken down in a progressive system components, and this is how we design it. This is how we sell it. Each one of these sections needs special consideration. And that's where you go back into our large engineering staff to do custom engineering, because each one of these segments are custom per install. And if you don't do it that way, we know that you lose either efficiency or functionality to some extent. And, you know, these lines, like I said, we have one out there that's 58 years old. So do you want to have 58 years of something that's not custom, doing the best possible efficiency and all the options that you can possibly have? So today, you know, we got a long presentation, and I want to take you front to back on these lines and give you an understanding of these different cylinders that make up a whole heat treat quench and temper line for tubing. First is your loading system, then the austenitized section that brings it up somewhere 1650 to 1850 Fahrenheit. And then we go into a dynamic quench that is controlled by the TTT curve. You got to knock it down, under typically 10 seconds from that temperature, from the surface to the core uniform to get the uniform metallurgy. A drain and transfer table, that's a table that usually is on an angle, and we'll show you pictures of it, but it has also a forced air side to it that blows down the ID of the tube, designed to get all the quench water out, because we got quite a volume, the largest volume aggressive quench in the world that we know of. And so this drain and transfer is a critical element. It also allows us to put a buffer in for metallurgical as quench samples. Then we go into a temper section to go back and adjust the hardness and the ductility with reheating. Then it has to cool in air, so it goes onto a cooling table. That typically our systems are a drag chain that the pipe is on there for hours. So then we get into the ancillary supportive equipment of the line, which is what we covered, the input transformers and switchgear, number 7, harmonic filters. Here in the US, we have a specification, IEEE 519. All induction equipment outputs a harmonic. And typically we're focused on the 5th, 7th, 11th, and 13th harmonic. We do offer harmonic filters that can bolt onto the power supply that we do a harmonic study, and we can filter out to this IEEE 519 coming out of our power source, which is your heaviest source of power typically in these facilities. All the rest of the equipment, any coating systems, anything else is typically on another transformer. So you have dedicated transformers for the induction, but we definitely control harmonics, and we do that so that harmonics don't come back into the equipment. MCC, the motor control centers, controlling the drives, controls, quench systems with the quench pit that I showed you some civil work, the towers, the pumps, the filters. So we're going to go over all of that. And then the water system, we have a contact and a non-contact. The contact is the quench, and the non-contact is for the power supply and the rolls and such. Now, when we look at a typical line, here's that panoramic view, not pandemic, that we're showing front to back. You have an in-feed system here to your left. And you go from your in-feed system, which is typically an incline table. We have paddle transfers that bring it over, or rotary transfers, and put it on a set of individually driven conveyor rolls. And we bring it together, and we butt it together right before it goes into the austenitize. And then the austenitize heating section here heats it up to that 16 to 1850 Fahrenheit. And then the quench system. And as you can see, everything is driven through here for precise control through the handling. It's critical. And typically we're on 5-foot centers. It depends on your length and your size of tubing for the proper support. Because as you get up in these high temperatures, especially above the magnetic Curie, the plasticity of the tube gets higher. So you have to support it very well to keep it straight and keep it from distorting. So then we come out and we go through the temper section here. This is an inline system just showing the rendition. This transfer table is typically put in right here. Then we go through the temper to adjust it. It comes out hot and gets exited onto the cooling bed. And the cooling bed then keeps the rotation and the feed. And typically pipes are on here for hours. And you got to keep them rotating and keep them feeding, which helps on the straightness. Here's a typical, what we call a U-shaped line, where the product is coming down in the bottom here. Here's a set of paddles that it takes off, transfers over to the conveyor line. and then it goes through the austenitized coils. And if you look at the power here, the Ajax Pacer T is a transistorized unit, IGBT, 2200 kilowatts at the 500 hertz. That 500 hertz then gauges that depth of penetration. There's another factor here that you got to consider, and that is what we talked about in the basics of hysteresis that happens above the magnetic or below the magnetic Curie point. The other element of that is below the magnetic Curie point, the depth of penetration is very shallow. And after it bridges the magnetic Curie and becomes non-magnetic, typically in this second section coming out of this first one, the reference depth of penetration gets 4.5 times deeper. You lose the hysteresis heating efficiency, so you lose a little bit of efficiency after the magnetic Curie, but you definitely gain that depth of penetration, which helps you on your delta T, the uniformity. But you can see here, the point I want to make is you've got a 500 hertz here on that first power supply and a 1 kilohertz. So the 500 hertz helps you with that depth of penetration. Even though it's shallower below the magnetic Curie, we can go with a lower frequency to help us get as much depth as we can on this front end. And then we come into the quench components. Then it's transferred over to an incline transfer table with an ID blowout. And then this item 10 is the sample table I was telling you about. We can off product here every so often to take a metallurgical sample. A lot of these are driven rolls, so it'll go hit a stop, and then you'll have a plasma cutter, the latest technology, that'll cut a metallurgical sample off to go to assure, because there is some chemistry changes throughout different batches. But it's just a quality control. And then we can take that pipe and build a buffer on this line, open gap with the controls, and put that back on so that it could be run through the temper. And again, the temper is primarily below the magnetic Curie point. So we tried to make the power supplies the same frequency for redundancy in parts, and it works out very well. And we've got great simulation software that allows us to do that. So it goes through the temper, comes out hot, most times 1,000 degrees to 1,250 degrees. And we talked about a 0.3 carbon typically is going to be around 1,300 for the magnetic Curie point. So this is all below Curie heating. Then we off it onto the, with paddles, onto the drag chain cooling table. So that is a typical U-shaped configuration. You see the quench pit, open tower down here. We do closed towers there as well. Closed cooling system for the more high purity water, because as this hot pipe comes out, here it's quenched out, but all the way through this austenitize, it's getting hotter and hotter. So you got to water cool the rolls. Same thing all the way through this temper and all the way out, you've got to water cool your rolls. All that's put on this closed tower here. Here's another line, how it looks, typically a U-shaped layout. These items on the cooling bed here are what we call forced air convection fan systems. And on the cooling bed, you can austenitize, quench, and temper, and then it comes onto this cooling bed. And for the first half, let's say till the product gets cooled down to about 1,600 degrees in open air, you want to keep a rotation, and it has to just cool down in open air naturally. But after that 600 degree point, you can pour the coals to it. So we have these forced air convection fan systems that go underneath the cooling bed that can aid in cooling down. Now, where that really shines is when we're retrofitting an existing building, or we're taking out a heat treat line and we're trying to increase its throughput, and you have a fixed width. This forced air convection fan system allows us to go with a lot shorter cooling bed and accomplish the same goal. The other thing it does do is it allows us to put a coating system. Usually there's a water base that's put on an API product after these heat treat lines. And we can control the temperature close enough on that, off that cooling bed, that we don't have to reheat it, which is the normal for coating systems. The only time that gets a little squirrely is when you have to stop the line, but you can keep that cooling bed going, and it's a cooling process. It's not a heating process. So you can keep that going and empty that whole cooling bed and run it through at the temperature through that coating system. And it cures out the coating before it gets put out of the system. So here is another type of line. It's an inline system. Same components, except it's a lot longer. That's where the U shape comes in. It's wider, but it's not as long as the inline. But again, you have an entry table, fed in front of the austenitize, the quench. Item 8 is a transfer table over, and then you go through the temper, sample position again. Right here now off the cooling bed. These people didn't necessarily, they have a position here for as quench samples, but they wanted a sample table here at the cooling bed. And then it goes across the drag chain cooling table. Now here's another line, a U-shaped line. You can see the forklift here bringing the pipes in on an inclined table. It's brought into the system through the austenitize, goes through the quench system here, through the transfer table. Here's the sample position in this system. Then it goes through the temper. But then here we have a 6-roll straightener. A lot of our lines on the lower tonnage doesn't require a straightener, but we encourage customers to build in the conveyor section so that at any point that you need it, you can add it for just the cost of the straightener, basically. If you don't have the conveyor sections in here to allow this adaptation, there's quite a cost, and you don't know if you can fit it in your building. But this is one of those systems we were trying to fit it inside of a building. So we used a series of forced air convection fans. But again, they didn't begin until we hit down to about 600 degrees. Then they had a coating system over here somewhere, not shown in this picture. But again, we provided all of the transformers. This was from a 25 kV. But you can see the austenitized power again, 500 hertz below the magnetic Curie, 1000 hertz above, 500 hertz in this is a single temper system. We usually like to have a couple power supplies on each one so we can take an infrared reading in between them and adjust the second power supply as needed. And typically that comes in, if you're up in the north to Canada, your ambient temperature, these pipes come in with a lot of snow on them and been sitting out in the cold. You can go through this, say, austenitize, and in that second unit, you can adjust for that with a 0 to 10 or 4 to 20 milliamp or step control of the power. And it also helps metallurgists love it because of the ability, if the resistivity or the chemistry changes on the infeed between different manufacturers of the pipe or different batches of the rolls made to form the pipe, they can compensate for it here. So here is just a brief single line showing the 1247 3-phase 50 hertz coming into a high voltage switch fuse, and then input transformer at 2500 kVA down to 480, which is typical. And then we come into the power supplies, capacitors, and to the coils. Here is the water system diagram for these big systems. And on the power supplies, we'll show you some pictures. We typically have a side mount water system because the high purity water needs to be in the power sources because there is a DC section. And the DC section has the potential of electrolysis across its bus. So you can electroplate, basically, eat a fitting up and deposit it on the other side and plug it up. So we put a little water system on each one of the power supplies that just, you fill it, a lot of them are filled with distilled water. And it has a heat exchanger that then pumps within the system back to the tower and the pumps to cool it down. The coils are on that water. Water-cooled leads. Now, water-cooled leads are important because they're a mesh on the inside, and they're great water filters for anything going down through that water. They're going to collect right there. But the V-rolls we talked about, the water-cooled ones, are also on that circuit typically. So we're just going to go over the now a general description of the heat treat quench and temper lines. This is a video of an install that we did here in Texas back at the end of 2019, the beginning of 2020. And just to give you an example, we're installing and starting up our third system for 2020 in January. 2018, 2019 were big years for these kind of lines, and it really helped us through the 2020 down period in the economy to be able to keep that backlog. We're still working. Now we're hopeful. We got some other projects on the docket for 2021, so it looks like it's definitely not going to be anywhere near the fluidness of the market in 2018-19. But we're very hopeful. So please watch this video. It's a little long. It'll take you front to back on these systems. I'll try to narrate as we go through. There's just a little bit of music here I'll turn down as a promotion video. So let's watch this so you can get a real bird's eye view of the lines we've been talking about here on drawings and things. You'll get to see the physical front to back, including the quench pits. Okay, here's the in-feed table. This is a walkthrough of a 15 ton-hour line installed in 2019. We'll get a little bit closer look up here, but this is the austenitized section. The blue building, or the blue room to the right, is the operator control panel. What's directly below you here is the temper line. It's a U-shaped line. And as you can see here, the pipe is butted very nicely coming out and all the way through the induction coils, which we talked about earlier was critical to the uniformity. If that gap gets too broad, you're going to do a current crowding and overheat the ends. Here's the temper line, just daisy chain the water-cooled cables together in parallel series arrangements. This is the second temper power supply right before it goes to the cooling bed. But you can see the water manifolds running the length of the line that jumps over to the coil, water cooling, because each coil has multiple passages in it. The water-cooled cables are just cable trayed over. Very straightforward setup, very easy to maintenance. Now this is the cooling bed to the right, and to the left is the in-feed table. With a stop, as you can see, the pipes were held back. And here is the walkthrough from the front in-feed table. The paddles deliver one part at a time. Each individual roll is driven. Pipe is rotated continually and fed forward. The centers between these rolls are about 5 foot. You can see photo eyes there to the right that identifies the front and the back of the tube, so we can, in the controls, keep them butted. This mechanism here is a brush for rusted pipe that comes in off the yard. Now we stop the line here so you can see the butting of the pipe together. Here in about the third coil you can see it there. It's very nicely butted together, which is important to the so we don't get into the current crowding that we discussed earlier and overheat the ends. There's an infrared coming off the first power supply that we can feed forward and adjust the second. And you can see the progressive heat here very nicely as it gets up to the end austenitizing temperature anywhere from 1650 to 1850. Here's that aggressive quench barrel system that we have. You see an infrared right there at the tail end. And you can notice there's not a lot of scale on this, even though the temperature is elevated above the scale formation point, which is typically around 1400 degrees. In comparison to a furnace, it's just much less. But the IR units have to have a decay rate, so that's more of a little averaging in case some of the scale does get picked up. The quench height is adjusted by those jack screws you saw on the bottom automatically through the controls. Now you can see the volume of water coming out the tail end of that quench system. Got quite a volume. You got a river flowing here. But again, when you look at the TTT curve, it's a very aggressive process. You need this flow and this aggression. And you can see the adjustment, the jack screws underneath the whole quench assembly to keep the quench centered. The photo eyes here identify the front and the back of the part, and we speed it up so that we can take a part off with these paddles. You'll see pick up to transfer the pipe to the transfer table. There you go. Just roll down, drop down onto that drag chain. Then it goes, that table here is inclined, and you have right in front of you the ID blowout, air blowout of the ID of the tube. Very simple mechanism, very effective. There's a stop on the tail end because a sliver through there could come out pretty aggressive with this ID blowout. But as you see with the photo eyes, part is now exited off of that transfer table, and then it's raced up so that it can catch up with the tube that's processing prior to the induction coils so that you don't have that current crowding. But look at the level of controllability here and our engineering's ability in the programming to adjust this line precisely. You can see that tube just touches each other. Now they kind of roll on each other because the cut is not exact, but it's good enough. And like we talked about that current crowding, we can have, as a rule of thumb, up to a ½ inch and not really get into overheating the ends. And or we're lower frequency here, as we showed with the FEA. That also helps with that current crowding when you produce a gap between the pipes. But you can see here it's very precision controlled. We like driving every roll. We do have systems with daisy chains together, but when we did a cost analysis, we found there wasn't enough price difference to lose some of the functionality of having individual drives here, especially to keep everything driven and maintain this butting together. Here's an infrared to the right that's reading out of the first power supply, and again we can feed forward to make adjustments to the second power supply in the condition that the ambient temperature has changed, the resistivity of the base material has changed, and that's a very nice versatile tool of induction, as you can adjust it, feed forward the next power supply if you have multiple power supplies in the line. But you can see in the control, it's just very nicely controlled all the way through these induction coils. It's progressively heated. The temper typically gets anywhere from 900 and some degrees to 1350, depending on the alloy. And here's the final temperature infrared monitor to feed back to the controls. Not so much of a scale issue here because we're below that scale point of 1400 degrees. So it's more of a 1-to-1 here in the temper, but now you can see it start to separate. The photo eyes identified the front end of this pipe, and it identified the back end here, and then it starts separating. As you get smaller lengths of pipe, this separation happens a lot more rapid. It'll drive this pipe forward a lot quicker so it can get to the end stop, so then the paddles can transfer it over to the cooling bed. But you can see there it really starts separating pretty good. Here's the pipe exiting on the rolls prior to the cooling bed. Now, you know, this pipe remains hot, so all these rolls are water cooled here on the ID of the shaft. And then it's put onto this drag chain table, and it sits there for hours basically. And again, like we talked earlier, you have to keep it rotating continually till you get down to about 600 degrees, and then you can wrap and cool it. In this particular install, we do not have the forced air convection fans. The cooling bed is 60 foot long, adequate for the 15 tons an hour, just in open air. You see the paddles raise, they lower down, the pipe goes on and hits the dogs on the chain. Then it's just continually fed and rotated. And you know, there's quite a range of parts that run on this line. So going up the 7-inch, the pitch between these dogs. It doesn't keep it rotating 100%, but it's adequate enough to help on the smaller sizes control the straightness. A very simple drag chain design with quite a bit of supports in between the drag chains. Again, we're trying to keep this and help with the reduce the deformation and keep this pipe as straight as possible. So it rolls forward, comes down here to the end. As you can see, it rolls. It doesn't keep rolling 100%, but again, it's adequate enough not to get into too much cost. We do have a walking beam on the front end that will fast rotate the pipe, and some people swear by that. But you're talking several $100,000 of additional cost into the cooling bed for that. As you can see here, it just continues to roll. It drops off, gets kicked up onto this exit conveyor. It then takes it over and it gets coated in line, and then it has a hydro tester and a stenciling machine on the other end in that other building there behind. So now we're over to the transfer table of the U-shaped line, and here is the position for the as quench sample position. That set of paddles will lift a pipe off of this before it goes into the temper, and then it's fed to a stop on the front end there where a plasma cutter will cut off a sample. Then it's reversed, and then a gap is built on this transfer table to put that cut sample pipe length back in the line so that it can run through the temper and be counted as a good pipe at the end of the day. Here's on the entrance side of that transfer table. We're going to start showing you the pit, the trough here for the quench. We have that aggressive quench, a lot of flow here. So here's the trough. This was an initial startup. We had to drain this quench pit a little bit. It was a little too high. But here you can see the diverter walls that divert the flow of the quench and the scale down into this quench pit. And we lowered it about 6-8 inches, and you'll see here in a few minutes in some drone footage where the weirway walls are. But here's a common pit. We have a evaporative tower to cool the quench water down. There's typically a element heater in here just to maintain this quench. You try to maintain it in the high 90s Fahrenheit. This is a centrifugal separator. The quench water comes into a scale section, and then it drops over to what we call the hot well. And the hot well has a vertical pump that then pumps the quench water through that Lycos centrifugal separator. Here's a back flush at the back of it here that goes in just a regular tote bin. But it drops back through the top of that tower after it goes through this centrifugal separator. And then the two pumps you saw to the right there pumps it back through this fine particulate matter filter right in front of you, the brown filter, right before the quench headers, which you can see are vertical here with individual flow control valves to control the pressure, so we can equalize out that quench all the way around the circumference of the barrels and the rings, and that compensates for any 90s in the plumbing or longer runs. That's how precise you want to have that quench. This is the water system, a dual pump for the closed pressurized power supplies, the rolls, the coils, and you got a dual pump. One goes out, the other one kicks in automatic. Now here's the drone footage I was telling you about where you can see the weirway walls. The quench comes down that trough into that first cavity where all the scale is put in, and it spills over into the second cavity there and then goes over into the hot well, which has the pump for the centrifugal separator. You can see the pump here and the weir in that concrete wall. Again, this was on the initial startup. This is a footage that is we were targeting because it just wasn't available. Here's the quench pumps, the two vertical pumps, as you can see, go down into that cold well, as we call it. That's after the water has gone through the quench water has gone through that tower. Here's the trough on the infeed side from the transfer table. It has containment walls all the way around it. This was an existing facility that had induction in it that was taken out and the Ajax Taco put in. So the containment walls are a little high here than what's normal, but the concrete retainment walls just make sure the quench goes back down to that trough and into the pit. And they're a simple drag chain. As you can see here, a very simple mechanism. But to the right, you can see that sample position where we drive the pipe forward and plasma saw cuts it off. There's another view of that. And where we can actually pick the pipe and put it back up on the main drive rolls that you see right here. This was before the roof was on this building, this side of the building anyway, where we extended it, the operation. You can see lifting paddles to your right and to your left. And this is an incline table. Straight up ahead is the ID blow-through mechanism. That just blows through the ID of the pipe and assures the quench water's out before you go into the temper. You can see this install was done with CPVC. This is going into the austenitized line right in front of us here. The temper is to the right. You can see the ID blowout fan system there. Now we're going to walk down the input side. Here's the input transformers and switch gears. We have a transformer pretty much for each power source, and the ancillary equipment is put on one. The temper is two temper units are on one. Here's the in-feed table. It's an inclined table with a stop about halfway through it to slow down the inertia. They end justify here with the forklift. They don't have the end justification mounted yet, but eventually they did. The power supplies, we're going to look. This is the vault, the austenitizing vault. Our units do not require to be put into a vault. But again, this was an existing installation where the other equipment that was in here did require that. So we just went with it. I mean, they had everything available, so why not? Here's the water-cooled cables of the output that's put into trays and transported out to the induction coils. They're cross-polarized to bring the magnetic field inward to control its overall outputting size. This is your incoming power from the transformers we saw outside. Some ancillary disconnects there, breakers. This is the austenitized 2 power supply. They're 2,500 kilowatts. They have harmonic filters mounted in the cabinet themselves, and the components of that harmonic filter is water cooled by the cooling water of the power supply. This is a transistorized IGBT power supply. Here's the control room, the little blue room to the right of the austenitize I mentioned. It has HMI and manual controls. Here we're going to just run through the HMI. These are the line drives telling you all the drives are working. No limits or conditions. Goes to the austenitize, the temper. Transfer table, cooling bed, all gets its own screens. This is a recipe screen. You can store all your different sizes and wall thickness and material setups. This is a memory recall screen for troubleshooting. It's very nice. Here's your motor drives, VFDs. And here's your individual power supply screens that come up. Shows you its power level, its temperatures. Here's the water system. Pretty straightforward controls. And we have several different levels of controls here and graphics. Depending on how you watch your line, a lot of people have multi-monitors, at least 2 or 3 monitors, looking at different points, say on a cooling bed, which is a little difficult to see from that control pit the way they had it. This is a side mount water system that we put in and recommend on our power supplies. They're high purity water with low resistivity. Most are filled with distilled water. And it just breaks out any potential of contaminants coming through in your high dollar power supplies here that's sensitive. They have a DC section. So you have electrolysis potential across that DC section, which is basically electroplating. So we solved that issue here by putting a small water system with a plate frame heat exchanger and its own pump and reservoir and filter right at the power supply. And it's proven for a little extra money to be a great help on keeping that power supply as clean as possible. Here's in the motor control room, which is located adjacent to the Tempur power supplies. And again, it's all in a vault. It was an existing installation, like I said, but they already had it. It was mandatory for the other competitors' harmonic filter and power supplies, but our Ajax units are built so they can sit on melting decks and be right behind liquid metal by not so far, and the meters are even melting off the cabinet and the things will still run. So, but in this environment, it's only better. So, pretty straightforward operation. This is located by our Longview Service Center in Texas, close to Lone Star, Texas. These are the drive panels, the motor controls. Here's the Tempur, the T2. This one is a 1500 kilowatt. Here's another line that we started up about 2 months ago down in Houston, Texas. Again, this is the sister line, 15 tons an hour. And again, the power, so this was a greenfield operation. The power was put in volts as well as the other. This is the Austinitized line. Here's a quench system. You can see a better view of it in this drone footage. Here's the transfer table. Here's the paddles lifted up. You can see the pipe butting together here on the Tempur side. So very short video there. So back to your question, is this process suitable for all API steel grades? We do L80 and P110, which is the more difficult API grades. There's different temperatures, there's different feed rates. Which holding time at constant T can you have on the tempering furnace? To homogenize the temperature on section and on the length. That comes into a question on the Tempur. You know, it's below the magnetic Curie, so the reference depth of penetration is shallower. So versus the Austinitized side, your delta T is broader. We have found we can go higher in temperature on the Tempur in a shorter period of time, and then we hold that temperature in open air till we get to the cooling bed. Then it's put on a cooling bed and it's brought down to 600 degrees before anything is done. So that's all open air timing. We temper with the same metallurgical structure on the tempered martensite uniformity to a 95+%. So it's very comparable to a furnace, but we do have to bring it up a little bit higher. So hopefully that answered your question. And the API steel grades, yes, we can heat it. We do even stainless steel annealing and things, complete non-magnetic. But in API steel grades, the delicate grades, the P110 and the L80 has special parameters, and you spend a little time setting that up. But there is a open air and a higher temperature we get to. Now, we talked about those lines running, both lines are made for upset processing. The inline upset tubing for tube and pipe, you have a thicker wall in the upset. And then it's tapers down and goes to the body. The traditional way to process upsets were to preheat the leading and the trailing end. But when you do that and you put it on the line and you've got a 48-foot long pipe, you end up with a differential between the ends and the body. So through FEA analysis, as we were showing here, we were able to come up with what we call a frequency scheming for upset tubing, where we can actually heat the upset first, that thicker mass. Remember, we said the lines of flux we can separate by frequency. And we use that to heat that thicker mass. And you can see that the tube of the upset is going to be closer coupled to the coil. So we precisely control that so that we can heat those upsets just about perfectly uniform to the body, and a proper delta T to get the same heat treat, quench, and temper metallurgical results. As you can see here at the lower right, I'm actually going to show you a video next of Apollo tube down in Brazil. The line's been in probably about 12, 14 years now, and they run upsets every day, and you can watch that frequency scheming work. So again, don't just take my word for it. Let me show you one, how it's working here. This is the end feed table. Bring the pipe in. You can see the stop on the back, just to slow down that inertia. The pipe's going forward, and you keep a buffer in the front of the line so you don't ever build in a gap. Now you'll see that this is a rotary transfer, not a paddle system. On our higher tonnage lines, we use the rotary transfers. That's out of the way quicker. But you saw that pipe race up and touch that pipe going before it gets into the austenitized section. One is always queued up. And these rotary transfers are a lot more expensive than the paddles, but they're critical on the higher tonnage. But here you're seeing the austenitized heat, which you go to the highest temperature, so that'll show you the uniformity of this upset. And we do the same frequency scheming on the temper. But watch this thing go through. You can see it right there. Okay, it's not exactly to the same temperature as the body because you got a thicker mass there, but it's progressively being heated. Here you see just about dead uniform. Then it goes in right out of that last coil. You can't tell a difference. So again, proof in the pudding there, so to speak, showing you, not just telling you. Oops, let me get that. This is seamless. You know, we talked about the L80 and the P110 and the upset effect, but there's also a condition with seamless. And traditionally, seamless has been all run on furnaces because API allows a very broad variation in the wall thickness. And that variation equals to additional hooks in the pipe. And so we did a joint development project over a couple years on one of our lines with US Steel here in the US and on seamless. They were running seamless through an ERW design line. And we discovered everybody was more concerned about the thicker wall in the variation, not heating it through, but that we could compensate for with power and the frequency selection. It became the thinner side of that spec that overheated and caused the pipe to hook. So, you know, where most of the surface heat is below the magnetic Curie point, what we did was the algorithm that we came up with together through this development came out to reducing the power density below the magnetic Curie. Below the magnetic Curie, so we slow it down there and then pour the coals to it. When it's above the magnetic Curie, where that depth of penetration is 4.5 times deeper. And here is a delta T curve. Each one of these spikes on this curve is where there's an induction coil. And then here's the fall of the surface is the gap in between. And then it races up again. Then you get up to the magnetic Curie point here. And I mean, you can really, where we're pouring the coals to it with additional power density, but you can see the dotted lines are showing the maximum and minimum of the API spec on seamless tubing. So we can run seamless tubing. We have to lower this power density in the front end to do it. And that reduces the line speeds typically. but there's scheming we can do with a little bit longer line. So we can and do and have, and most of our lines run parallel seamless tubing as well as ERW. So the line makeup, as we showed you going through the line, we bring in line utility power. 12,470 is more common here in North America. And then we step it down to 480 or 660 volts. And then we deliver it across our AC to DC to AC converters, our power supplies, as we call them, that's pulsed to semiconductor devices. Here is a harmonic filter. We actually have a company called Control Transformer that makes our reactors, and we make our own harmonic filters that we bolt onto our power supplies that filter out the targeted harmonics that's outputted out of the induction, which typically we're focused on the 5th, 7th, 11th, and 13th harmonics. But this compensates with your high power demand power supplies, compensates for the power supply. So, and the significance of this is that, you don't have to have other manifolds and water drops. This bolts right to the power supply, and everything is water cooled. Some of the vaults that you saw were required on competitive equipment because they had aftermarket or other vendor harmonic filter system standalone that was not fully water cooled. And they had to air cool them, so they had to control the air in that vault for this and other things in the power. So we water cool everything, so everything's controlled, and that's the way to engineer bulletproof, as we like to say. Here shows that water system bolted onto the power supply with a heat exchanger, pump, and a little reservoir. We do, like I said, the Pacer power supplies, IGBT and SCR. Emity can make these power supplies to the CE rating for Europe. They also have their own power sources. Here's an end justification system on the front of the line coming off of the incline feeder. This is a more sophisticated, where the pipes are brought onto a conveyor and then brought to a stop and then brought onto the primary feed conveyor you see to the right here on the line. So this position right here is an end stop to end justify, so that when it comes into the photo eyes, there's a common point. But this is driven, so it can go back and forth and get the end justified. Now, on the other system I just showed you, they just basically have a plate on the infeed table, and the forklift driver comes up with a pipe, and they just hit the whole stack of pipe on their forklift. They just then justify it and put it on the infeed table, and that works also. Here's the one we saw, infeed system at Apollo. Conveyor sections, again, we like the thing to have bearings on the end and be supported. There is cantilever designs out there. There's also designs out there that daisy chain the different rolls together. But again, these lines, when you have pipe coming in and you're going through the auxitize, not all that pipe is perfectly straight. And when it goes to the auxitize, it sometimes gets squirrely with the stress relieving. And, so you're hitting on these rolls quite often. So the cantilever design does work. We can offer it, but all of our lines out there have this bearing at the end to fully support that roll. And we believe it's truly helps the alignment of this line, which is critical to the straightness on these lines. And again, we analyze the daisy chaining of chains and these drives, multiple to one motor, and there's a cost savings there, but there's not enough, we don't believe, to lose some functionality here on controllability. Again, in the austenitize, we're looking at an as-quench martensite structure, grain structure to the right, and the uniformity coming out of our quench is 95 plus on the uniformity of that grain. And typically we get within 1 or 2 points on the Rockwell scale uniformity. The quench is the major component here. And I'll show you on the TTT curve. I mean, the AC3 line Um, you have to bridge that in temperature and then quench that thing out very rapidly. And then we're looking for a tempered martensitic structure with a very uniform grain coming out the end. And that's where, again, the question was, and questions come up, especially people that are used to furnace specs and working with furnaces that just soak that pipe. The furnace lines are a lot longer, a lot more costly because they heat on a surface and they conduct all the way through. Again, even though we're shallower below the magnetic Curie point for tempering, we're still inducing current at a depth of penetration, so we can put more energy into it without overheating the surface and heat it more rapidly. And we have found we go a little higher in temperature in the temper, and we match the same metallurgical results, or at least close enough for acceptance throughout. Now, we have done preheaters on temper for furnaces to people that want that and feel that they make a better product that way. So we work either way. The 134 ton an hour that we're putting down in Houston, starting up in January 2021, that does have preheaters for the temper and then a furnace afterwards. So we can work both ways. That particular line goes up to 13 3/8 though. So, it's a lot thicker wall also is another reason they did that. But you look through the austenitized line that we showed from afar, and you can see here is a 2.4 megawatt power supply with the harmonic filter and a capacitor section built into the power source. Here's your infrared pyrometers after that first bank and after that first power supply, which again is 500 hertz. So we can feed forward and compensate here for any metallurgical changes in the base material, or again, the northern snow effect. Here, a typical coil is 28 inches, and the distance between the centers of the rolls are pretty standard around 60 inches. A lot of our lines, most of our austenitizing lines are built on a 1 degree slope, so that any quench water on our very aggressive quench, if there's any gaps and it gets put into the inside, because it's not a perfect seal by any means, and we're really throwing the coals to it on pressure somewhere. We have lines running at 7 to 10 psi on the individual circuits on the quench, going up to 35 to 40. So the 1 degree sloping helps us keep water from going back up into the coils. And when you're heating the pipe to 1850 degrees, water spraying on the inside there is going to thermal shock and break the aluminum refractory out. So here's a typical line. This one is rated at 36 tons an hour. Now, this slide makes some people very uncomfortable. If you look at the lower left and the upper left, you'll see a very small diameter tube running through those coils, and compared to the right. And everybody that sees that, even competitors, look at that and say, man, that's just horrible. Your efficiency has to be horrible. Your uniformity, absolutely not. The current, you got to understand the process, and the current runs around the circumference of that tube. And if you've got a broader coupling at the top and a real tight at the bottom, you lose efficiency here, you gain it down here. Increased efficiency. So it's pretty much a wash, not a one-to-one, but it's pretty much a wash. And remember, the pipe is rotating as it's feeding, and that becomes one of the key elements. If you rotate 2 full revolutions in the coil, you have enough length for the throughput that you're running. But if you have 2 full revolutions, let's look at this condition of a 1/2 inch coupling at the bottom and a 2.5 inch at the top. If you stop that line, you'll see stripes on the bottom where it's overheated, like this thermal rendition here on the pipe. But if you have 2 full revolutions of rotation within a given coil, you get that condition right down here at the bottom where it uniformly heats, that efficiency offset. So what that allows us to do, and even though that's uncomfortable to look at, it allows a broader mix for a given coil design to run in the coils. Because, I mean, if you look here at all these coils, there's quite a few. Now you want to change this out and put another set of coils on there. We do have cassettes that you can lift off with a crane the whole line at one time, but that's a lot of additional cost up front. Ajax Taco built in a conductance window in the power supplies, allows us what we understand is the largest conductance window in the industry, to allow us a lot more versatility here. And understanding the process as we do, being, providing them for 7 decades, I mean, we truly can run a very broad mix of product through here with this design. So, you get into the induction coils. The upper right is a coil that is encased in refractory, as you see in the lower right, that you've seen on our lines heating. But this is what's inside of there, and it's fluidized bed coated or electrostatically powder coated with a nylon, and then encased in what we call a cast brick coil. And we did that because once upon a time, all of the coils had end plates and a mechanical structure. And the end plates that see all the heat and the thermal stresses was made out of asbestos. Well, that's been outlawed in most manufacturing, just about all, I think. And so the replacements of the NAD11, or the Transite 2, as they call it, is all a silica-based material that doesn't have the mechanical properties or the thermal. So we tried it for quite a while, quite a few years, and then we punted to this cast brick design. And, people say, oh, man, that's a lot more cost. No, it's not. You're making a mold, you're pouring the coils on the inside anyway. It's just a little bit more raw materials, but a lot less than buying all these high temperature boards that now do not hold up. To the left, you can see that 1 degree slope. These are coil stands that block goes on top to keep that quench water from creeping back up. So now we're going to look at the quench system. Our basic design is a barrel and ring concept that we've been using for decades and decades, and we've been challenged over the years, but the bottom line is this system was contoured and designed to the TTT curve, the job that it has to do, which is very aggressive. Here's the quench now. When we talked about that 2 full revolutions of the induction coil to normalize out the heat, you don't have that effect here in the quench. The quench must be aligned on the center of the pipe to get uniform heating all the way around. To that end, our quench barrels, we have 4 baffles in there, and break it off so you can individually control around the circumference of that barrel and equalize out any differences. That's what's critical to getting the end metallurgy uniformity and the AsQuench sampling. Here's the quench barrel. The upper right, the lower bottom shows that aggressive quench, throwing quench everywhere. But we have containment systems that control that, but you see a grating in the floor. Now here's the TTT curve. This is where our quench was designed to. And the bottom line is you have to quench that thing out below this MS point to get a uniform grain structure, martensitic grain structure. And as you can see here, the time to do this job is roughly 10 seconds. So you're really working hard in those first couple, especially in that first barrels where most of the work is done, the first, and we have a second. But our quench is a series of small holes that make up a wall of water that is just pounding this thing. There's others that have big openings and they flood quench at a single point of impingement, and it deflects up, and then you have another one and another point of impingement. But if you do a thermal video, which I have, looking at that design, you can watch the temperature creep back up in between these points of impingement. And the argument was that we have real fine holes and there's scale in the system, and that could clog it. And I'll address that here in a minute. But the bottom line is you start getting out of this window at this MS point, and you start getting into a differential of grain, mixture of perlite, bayanite with your targeted martensite metallurgical properties. So the desired, and like we said, we typically get 95+% martensite with our uniform heat, which is required, but the quench is where the magic is made here. The real work is done. And one of the main elements right out of the gate is you have to power past a vapor barrier. I mean, it's like any piece, something hot, and you stick it in or pour water on it, it's going to dance on the surface. So you have a vapor barrier that you have to power through to get to that MS point first. So now you see that aggressive TTT curve, and then you have a condition where you're not actually quenching until you power past this vapor barrier. And, just looking at a 1/2-inch wall on a 5-inch diameter pipe going up, up here close to 1800 degrees. I mean, to quench that thing out uniform on the wall thickness, I mean, it takes an aggressive quench. But this is a curve to our quench. And again, the science isn't exactly 10 seconds. That fluctuates with the chemistry of the material some, but it's right around there. So you can see our quench design is very aggressive for some of the thickest wall you're going to run 1/2 inch through these lines. So that's why we've had our quench for decades, and we make it up the way we do. Now, this is just another show of time and different points for different grain structure mixes as you increase the time it takes to quench out. And again, you get a mixture of perlite and martensite in the grain structure or bayanite, and it's just not desirable results. And that's what you get out of non-aggressive quench systems that don't consider that TTT curve and understand the aggressiveness that's required of this quench. So the quench that we made aggressive to the TTT curve is made up of barrels and rings. And again, these barrels, like I said, has small diameter holes, and that's where the primary work is done. Several years back, we got beat up by one competitor that said, hey, we came up with this big wide slot that just floods water to that single point of impingement. And, it's far superior than your barrels that have these little holes that clog up. So we took that to heart. I mean, these things are more expensive to manufacture by far than that big old slot. But at the end of the day, I went to Tenaris in Blytheville, Arkansas, where heat treat line 2 we've had in for 30 some years. And I went to their barrel and got their permission to take it out because this inside is a sleeve that's replaceable that has all these holes in there. And I was looking for that condition of plugging our holes, excuse me, and Tenaris, the operators, their maintenance group, everybody said, we don't have problems. That quench barrel's been in there for 12 plus years. So I took it apart and analyzed it in the field. And some of the holes were washed a little bit, but there was no material. The inside was just as clean as the day we provided it. So if you use a cyclonic filter in the pit and that fine particulate matter filter right before the quench headers that we design, you get 12 years out of one of these rings. It's a big value to have a very aggressive quench. You can see they're angled on a 30-degree angle in the lower left corner with that quench water on. And you can see the big hoses all the way around through the 4 baffles inside to get the uniformity and to be able to adjust around it. That's how critical this is. This is where the work is done. This is where your metallurgy is either good or bad. I mean, everybody can heat uniform for the most part. It's right here in this quench. So we have what we believe is a economical best solution, and it's been proven over decades and decades. And again, Tenaris then bought a new insert for their quench because I told them 12 years was a little long. And but at the end of the day, I went back 2 years later to try to get that insert that I could show people at a show. Actually, it was a Dusseldorf show, the last one that they had. And they wouldn't give it to me. It was up on a skid, and they said, hey, we were making good parts. If we have a train wreck somehow on this line, we're putting that sucker back in. It was still working fine. But if anybody has any question there on these holes or a competitive issue comes up, I do have that video where I completely took apart that quench and can show you. So we believe we have the best quench in the industry that produces good results. Quench containment, again, is critical. A lot of flow here. In our recent systems, we've actually made more containment right at the right past the quench barrels and knock it down, as you saw in some of the videos. The quench system itself is made up of, here's a general schematic. We were talking, you've got a collection pit around the quench with the containment walls that you saw. And then the water is brought back in a trough and dropped into the first cavity here, which is the scale cavity, where the bulk of the physical scale is collects in here. And this is cleaned out by a bucket crane or a sucker every 6 months to a year, depending on your volume. Then it's after it runs through the centrifugal separator and it goes through the quench, it's dropped back down. Well, the pump here in the hot well takes it out and runs it through that centrifugal separator to bring it through the tower. And then the tower dumps back into the cold well, as we saw in that one video. And then there's vertical quench pumps in this cold well that then pump back to the quench system. But when it's pumped back to the quench system through the typically dual pumps here, that's where we have that fine particulate matter filter right before the quench headers and the quench rings. So this makeup has been proven for decades. If it's done and the pit is cleaned out right, we've proven it with a 12-year-old quench barrel. When I took it apart, you don't have issues if you do your maintenance on the scale. And again, if you're comparing against a furnace, we have a lot less scale compared to a furnace. It's night and day. But there is, when you're cleaning these things out after 6 months to a year, I mean, you're pulling several tons of scale out of this thing. Here's just in our controls, the HMI, one screen that comes up that monitors all the pumps throughout this quench system. Here is the physical pits. You saw this picture earlier on. This is a in-plant quench system right below the quench line. This particular one was rated at 36 tons an hour, and you can see the weirway walls and the spillover in this pit. This is an outdoor pit that's covered with the grates. But again, just like we described, you got your scale collection, then the water spills over this spillway into the hot well, pumped through the tower and a centrifugal separator to get the loose scale out of the water before coming over here to the cold well and then pumped back through the system. Here's a vertical pumps. Here you see in the hot well, the pump pumping through the centrifugal separator in a tower. And here is your return vertical pumps. Here's a system, vertical pumps that were located inside a facility. Excuse me, usually that's done in the bar lines. And again, like I said, we do, the bar and tube lines are very similar. So here's that centrifugal separator to your left in that circuit. And here's the fine particulate matter filter right before the quench headers that allows us to keep our aggressive small hole quench barrels clean. And they all automatically back flush. I showed you in that one video, there was a cup at the bottom and they stick a 4x4 bin underneath that, and that collects the scale in an automatic back flush. Typically, this system here back flushes back to the quench pit on the scale collection side and automatically back flushes. Here's the infrared devices we use for temperature monitor and in controlling throughout the line. Complexity consideration, here's your drain and transfer, another view of that. Here's the ID blowout. The table itself is in a incline. In this particular application, this was a lower tonnage line, but the customer preferred our rotary transfers versus the paddles. So, for more money, these things precision pick up. They're out of the way within seconds. They deliver. There's less noise in the facility. So whatever your preference is, we can provide. Here's just another view of a drain table, a smaller one, in line on a smaller tonnage line. This is just a top view of that transfer table. Here's the blowout of the ID. It's just a chain-driven table. Again, everything is cold here, so you don't have to have the supports that you have on the cooling bed. Now we get into the temper side, and that's where Mr. Valzar and a few others made a couple questions earlier that we answered as far as the specialty alloys of the P110 and the L80 that we can temper on this line, but we have to have a different temperature setting and a throughput setting to get the right grain structure at the end. And again, just progressive heating. The temper line is basically the same as the austenitized line. Here you can see we have lower frequencies in this particular one of 300 hertz and 500 hertz, which goes back to that reference depth of current penetration we talked about, because the temper is all below the magnetic Curie point heating, so we're shallower in that depth of penetration. And here's actually the curve showing the AC3 and the AC1 lines for the quench. And, in relation temperature to time, we can adjust the hardness and we can adjust the toughness, the ductility in the temper by time at temperature. This is a chart showing what we talked about as far as the magnetic Curie point when we reviewed it in the basics. But for a 0.3 carbon material, typically that magnetic Curie point is somewhere between 1300 and 1400 degrees. And as your carbon changes, that magnetic Curie point changes. But again, I think it's in the next chart. Yes. Here we actually show you, if you're looking at a 1 kilohertz down here on the lower side, the below Curie heating for that 1 kilohertz is, 160 thousandths. You go to the above Curie heating and it's 4.5 times deeper. For the same frequency, you have 632 thousandths. So truly that magnetic Curie point is something that is needed to be understood. And definitely a consideration through our simulation software. When we produce those magnetic or the delta T curves, you can truly see the delta T collapse together when you get above that magnetic Curie a lot faster than the below Curie. And that becomes a tool that we use in the upset scheming, frequency scheming, as well as in the seamless we talked about as far as the wall thickness variation in the frequency scheming that we use there in the power density algorithm below the magnetic Curie. This depth of penetration is a critical element in the design of the line and its functionality. Temper runs in seamless. We talked about the joint development with US Steel on the seamless we did for several years and came up with that custom algorithm in the front end. Tempering is no different, the same thing. We got to slow it down on the front end. That's why seamless runs on ERW lines, but at a slower rate. I did have some discussions this week at Tube 2020 with a vendor that can actually, with a magnetic coil, actually look at that wall variation of the seamless. And on the in-feed side, before we make it up, we were talking about maybe putting that there and getting some feedback to help increase the line speed on seamless tubing because of that wall variation. Because if we can verify what the wall variation is, we can manipulate this power density curve to increase the line speed. Tempered discharge, showed you a video and we talked about the drag chain cooling. We do have a walking beam system on the front of this for fast rotation. Some people like that and swear that the straightness is controlled better down to that 600 degree point. but the majority of our lines just have a straight drag chain, as you see here. Here's a open air, very large tonnage line. This was one up around 42 tons an hour. And you can see multiple cooling beds. We come off, somebody asked if we had, how long they set on there. I mean, this pipe is sitting on these multiple lines for hours and hours here. Just air cooled. And we showed our forced air convection fans to help that. And here's a picture of it. And this shows, where we naturally convection cool down to 700 degrees is actually the spec. We like a little buffer there, so we designed a 600 degrees. But after that, if we're fitting into an existing building, we can pour the coals to it with these forced air convection fans and fit a higher tonnage line in a smaller existing building. Here's what those forced air convection fan systems look like. They are VFD controlled. So again, you can really control the output temperature coming off of this thing. And what that allows you to do is eliminate another induction heater at the end where you have to preheat going into a coater. And if you look up in this upper right corner, this is the coating machine. It's open right now. It closes down, the pipe goes through. But we can control how much cooling we have here to maintain below 170 degrees, but enough temperature in it to cure out that water-based coating material. Various drives, we looked through the line at the different photo eyes, the infrared units we talked about that control the temperature, and we can actually feed forward with a PID loop and control the power of a second unit in a multi-unit line for a variation in incoming metallurgy and or ambient temperature. Going into the controls, I've run enough of these lines over the years that we like to, in our engineering department, it's not old school, it's just what I say is sound engineering. A lot of people have gone to HMI and PLCs only. And, in the startup phase, and especially when you're troubleshooting and you're trying to work with a line progressive, these manual controls on the left adder to the HMI screen and PLC controls really gives you flexibility in the line, running it and maintaining it. HMI screens throughout monitoring the system, you can look at all different parameters and all of your recipes are set. You can set your alarms. Here's one option for an operator screen. It actually shows the whole line. It shows the austenitized line, the end feed at every position, sensors that's gauging the ends of the pipe, tells you if a pipe's present, and verifies the rotation and the line speed going through. Any given point, there's a stoppage or a problem. You can see here where this H15 is showing a blockage. So you can go right to the line, fix what's wrong, analyze it before you actually shut the production down. Here's just the temper line, and it goes to the cooling bed. Again, another screen for the water system. This is the closed water system. We talked about and showed the water system that's connected to our power supplies for the high purity water. This is just a monitoring of the dual pump. One pump goes out, the other will kick in automatically. Here's the cooling bed. Actually, both it's showing here, but there's one for the cooling bed and one for the end feed. This is actually the end feed with the stops here that slows down the inertia of the pipe rolling down because it is an incline loader. Here is a quench pit rendition from our HM1 HMI screen that truly shows the scale collection. Usually that weir weigh's a little higher, but the scale collection, hot well, cold well, and there is elements put into this quench water so that you can maintain a high end, because uniform spray in that quench is important, but typically they try to run it around 98 to 100 degrees. So up north, we have heaters that submerge in. Another single line here, just showing a typical amperage for a 400 volt input. MCC and drive panels we produce. We use a lot of Allen Bradley components here in the Americas. Here's the motor drives, panels. The quench system we saw is made up of what we call a contact cooling tower and pump system, and a non-contact for the high purity water of the rolls, the coils, and the power supplies. Here's what it looks like, a dual pump, another end view of that power supply water system with heat exchangers. Here's the typical evaporative cooling tower. You've got spray heads that spray the water across these coils. And this water spray is aided by evaporation. There's a sump under here that holds a volume of water to spray across these. And there is makeup water in this sump due to evaporation of this water. This is the closed loop water going through these coils. And that's it. Everything you ever wanted to know, plus with heat treat quench and temper lines for induction, both ERW and seamless. I'm going to run this video next week. The Tube 2020 show was extended through December 23rd. And so this recording today, I'm going to rerun that. And if you're looking at a pre-recorded version of this talk, please go to our company page at Ajax Taco. And at the bottom, there is a live video chat session. And I'll be there answering questions on any pre-recorded and replayed versions of this talk today. So thank you so much.